So when's our homework due? Friday. Yeah, Friday. And then again, as far as that exam goes, I'll probably make it officially due sometime after break. I have to look at my schedule. But if you like it so that your corrected version is figured into your midterm grades, stuff by early and stuff like that. Today and tomorrow might be a bad day just because I'm giving tests on my modern physics course and my physics in class course. I've pretty much been swamped almost entirely by them. After that, everything's, I think, normal. So, okay. So that said, I want to do a couple more problems of what we can do with these things. And then kind of wrap it up. And then we're going to start looking at circuits and what we can do with circuits and stuff like that. And that's one of the easier parts of the class. But it's simple, but it's still, the second test is going to have a lot of the stuff on, like with the gradient operator and stuff like this, and still similar stuff to what was on that first test. So you can't forget that part. Okay. So let's take an example here. Well, let's say here's the disk. Radius r, uniformly charged. I want you to find the voltage here. Find the. Okay, you tell me how to do that. Especially when we haven't had yet, we're going to have to work it out. Okay. Okay, so if I ask you for the electric field, what would you do with that one? I'll give you a hint. You're pros at this. What do you treat the disk as? A collection of rings. And so if we had the electric field for a ring, then we could just add them up. So what we actually do, we're going to do the exact same thing. We're going to treat this as a collection of rings. We're going to find the voltage for one ring, then add them all up. So we're going to treat the disk as a collection of rings. Then we're going to add them up. So the first thing we need to do is figure out what is the voltage for a ring. So let's ask, what is the voltage for a ring of radius r and total charge Q? So let's draw this picture. Here's our ring. This is R. Charge all the way around it. Now I want to find V here. Okay, you are pros at this. You tell me exactly what to do. If along the ring, what will we treat the ring as? Exactly. This is going to be a collection of point charges. So treat the ring as a collection of point charges. And again, this is another reason why I'm letting you do corrections on this, because guess what you're going to see on the second exam? Pretty much a lot of the stuff you saw in the first exam. And so unless you get that mastered, the second exam is going to be, we're not going to low. And I want, look, none of you are dumb. You're actually, it's actually, it's a good class. You just put in more time, you can turn this around. Okay. So you tell me what to do with this. I'm going to call it from here to here Z. Okay, what's the first thing you do with any of these pictures? If I'm treating it as a collection of point charges, I'd want to draw a little point charge. So I'm going to draw a little point here like this. Okay. And what will I call this little point charge? DQ. And we're going to say from here to there is R. Now, what did we say is the voltage for a point charge? AQ over R. So what will then we say this? I'm going to call the voltage, I won't call it V. I'll call it dV. So I'm going to have K. What is my Q? dQ. And then this is over R, where R goes from that point here to up there. Now, do I have to worry about X and Y components like we did with the electric field? How come? It's a scalar quantity, so it's a lot easier to work with. So if I want them to V for a ring here, I do that. Okay. You tell me what comes out of that integral. Okay. And the dq come out? No, we're integrating on that.
The argument,
How come?
because we're taking that precise.
Yeah, we're taking it along the z-axis here, so it doesn't matter where I am along this ring here. All the r's are the same. So we're going to have here. So this is going to be k over r. Then we go dq. But hey, if I take a dq, someone up along the entire ring, what do you get? Q of the ring. Now, what is this R in terms of stuff over here? Close?
I just need to.
R, Z, little r.
This is what I did.
Pythagorean theorem, excellent, good. Okay, so what you have here, is that right? This is your R, this is your Z. So this little r here is going to be the square root of r squared plus z squared. So I can put this in here.
But I get your.
Well, we never
Does that make sense? Okay, so you tell me how to take this and modify it for that picture. Come into my office and we chat on your exam. This is what I'm going to do. I'm going to put you on the at the board and have make you work it out. And what's the first thing you always do? I'm treating this as a collection of rings. But I tell you, I always want to see a picture. So what would I want to do in that disk? I want to draw rings. What do I call the radius of it? R poly prime. So if I come over here, I'm going to come out here some distance r prime. I draw a little ring here like this. And how much charge do I see inside this ring? dq. So now let's go through and figure out how to modify this. Okay. You tell me what that becomes then. From this equation here.
Over.
That makes sense? Our KDQ over square root of z squared plus r times. What's the technical problem with that integral? Right, so if I now want the disk, want view of the disk. This can be the integral of all these huge things. So what's the technical problem with this? R is not constant, and I'm integrating over the variable Q. This is KDQ. C squared plus R prime. So what's our solution to this? We introduce sigma. Okay,
That's what-
sigma is by definition charge over area. Okay, so the charge from my little ring there is going to be what? dq. Now, over what area is that little charge dq distributed? Okay, so I'll go over here. Let's have it in red, continue in red. Like this, shaded in here. I need the area of this ring here. So this has to be over the dA ring. Okay. Now what is going to be the area of that ring? Remember we said if I could cut it and lay it flat, it becomes a strip. What is the length of that strip? 2 pi r prime. The thickness of it we said is dr prime. And I said this has some thickness here. Dr prime. This is dq, 2 pi r prime dr prime. For dq, sigma 2 pi r prime. This pops into here. Okay, sigma 2 pi r prime dr prime over this. Now, where do I integrate this from?
0 to big O.
From 0 to big R. If this had been a washer of inner radius A and outer radius B, where would the rings go from? A to B. If this had been an infinite plane with a hole in it, radius R, maybe like on the exam, okay? Where would these rings go from?
Yeah.
Whatever the radius is, A, okay, then out to infinity like that. Yeah. That makes sense? Okay, so is everyone happy with setting this up here? Okay. Now, the rest now is just doing the mathematics of it. Okay, pull out all the constants. Okay, it's gonna be easier if I take this to the top. So I'll write this as the minus 1/2 power. And you tell me what that's gonna equal. What's the integral of that? What would you have to differentiate? Give yourself something going like this. Close. I gave you a hint. It follows the equal sign. Okay, so let's carry along with the constants. Okay, so we want to have what? Z squared plus R prime squared. The power minus 1. 1/2. So do you want the minus 1/2 here or no? Positive 1/2. Okay. Which one do we have? Do we have a plus 1/2 or do we have minus 1? What can you always do with an integral? You can check it. If you differentiate this, what do you get? On the minus sign, then this becomes minus 2, which is not something like the 1/2 power. If I differentiate something, so this is where. If I have a half. Okay, how do I take the derivative of a half? Take this down. And what do I do to this? Subtract one. A half minus a half is minus a half. That looks good. Then times the derivative of the interior, which gives me the z gives me a 0, and so this is 2r prime. The 2.5 cancel. Here's my r prime. So that's my answer. So this will be evaluated from 0. Okay. We put in the limits in Shazam, we have ourselves an answer. If I put in 0, that gives me this, equals z. Does that make sense? Think you're going to see a variation like this on the exam called test 2? Probably. Hey, there's a part B to this. Okay. Find E. How do you find E now? What's our brand new shiny method for doing this? Exactly. So we have this E, it's negative gradient of V, which is what? It's minus I hat, partial of the respect to X, V plus J hat, partial of V, respect to Y, K hat, partial of respect to V, Z. Okay, so what is the X dependence on V here? None, so it's 0. What is the Y dependence on V here? 0. Okay, that leaves this term here. So what am I left with? I'm left with minus K hat. Okay. And I get this fellow here coming down for the right. So this is my K sigma 2 pi. What is the derivative of this with respect to Z? Well, that's the same thing as Z squared plus R squared, the 1/2 power. 1/2 Z squared plus R squared. The minus half power times 2Z. Okay. Then minus. Okay. Choose go out, I distribute through the minus sign here. So this gives me this K sigma 2 pi times. Put this guy first because of the minus sign, 1 minus 1 over the square root of Z squared plus R squared. Let's see it. Boom. A lot easier than what we had before. That makes sense. Questions? There's a brand new part C, which you haven't had before. The charge, little q, is placed at rest at point P. What would be its velocity at infinity? So here's our little disk. Here's point P. I'm going to put a Q there, and this is at rest. It's gonna go off to infinity. So the question is, up here's infinity. Question is, what is its velocity here? Now, this one I haven't done something like this before. This is new.
Somewhere.
Think back to first semester. What does this smell like from first semester physics? We have a before and after picture. Smells like of energy. This smells like a conservation of energy problem, and it is. So you're going to say E initial equals E final. We're going to write it slightly different here. So energy is always your kinetic plus your potential. Okay. I'm going to take all the kinetics to one side and all the potentials to the other side. So this will give me minus U final plus U initial equals KE final minus KE initials. Okay, well, what's this side then? KE final minus KE initial. That's just our body. Delta E, delta kinetic energy. We're going to pull out a minus sign here. So this is U final minus U initial. Well, U final minus U initial is delta U. So another way you can write conservation of energy is this. You say any change in kinetic is going to be lost by potential. Okay, that's just another way of saying conservation of energy. But now here's the advantage. We have a delta U. Back when we started all this stuff, what was our original definition for the change in voltage? Good. So recall, we had the change in voltage is by definition the change in the electric potential energy over Q. So my delta U is Q delta V. I can take this, and I can pop that into here. Now we can use this. So what is this? This is minus Q, V at infinity, minus V at Z. Okay. Equals your 1/2 mv squared. This is your kinetic energy at infinity. Minus your initial kinetic energy, which is what? 0. Okay, what did we say? We always define the potential. I define the voltage at infinity to be what? It's defined to be 0. This guy right here is 0, by definition. So this gives me minus and a minus make a plus. So this is QVZ equals 1/2 mv squared. You should say QV at Z. And what is that? That's really this expression I was forced to erase due to a limited Blackboard space here. That's what we have here. Is the following. I have Q times. Okay, what was that stuff we had in front of here? Because I erased it all. No, we had a K, we had a sigma, we had a 2 pi. Square root of R squared plus Z squared minus Z. Is that what we had for the V before?
Yeah.
Okay. And then this has to equal then a 1/2 mv squared. So I'll just solve for the velocity here. So the velocity is going to be then take over the 2. So this will be 4 pi Q K sigma all over M. Square root of R squared plus C squared minus Z. All square root of all of that. What's another way I could have done this with the electric field? What would that electric field do to that charge? Because part B, we had an electric field. So what would that electric field do to that, our friend, the little charge? Put a force on it. And that force is acting over a distance. So what is that electric field doing to the little charge? Work on it. And what do you know about the total work from first semester physics? Okay, only if your force is constant. Okay. If you look at the total work done on something, it equals the change in the kinetic energy. Okay, so another way to do this. So another method. Is to use the E in part B. Okay, but I can say then the work done by the electric field is going to be this integral from Z to infinity of the force dot dl. And that's going to equal my change in kinetic energy. And this is what? This is nothing but this integral from Z to infinity of Q times my electric field. And I have this from part B, dz. And that'll be your 1/2 m v squared minus 0. And that's a lot harder to do. Because you have an integral and all this other jazz. But that'll certainly work. Okay. Makes sense? All right, let's try another one. I'm going to put a battery here. That's a 10,000 volt battery. This will become positive. This is negative. I have an electric field like this. I'm going to have an electric field. I'm going to have an electron right here. This is an electron at rest. The question is, when this electron gets to the other side, what's its velocity? So what is the velocity of the electron when it gets to the other side? You tell me what to do. This is actually going to be very practical, especially for those of you in engineering. Also, if you're a dentist. That sounds like they don't fit together. It turns out they do. Okay, what is this smelling like? Before and after. So you're going to think, I'm asking for velocity. It's an initial at rest. So it's going to smell like conservation of energy. So the way I'm going to write this, so this is going to be E initial equals E final. I'm going to rewrite this the same way we had it before. Hey, how do you think I'm going to write that out to you? So we know that this guy here is this Q delta V. This is changing net equals minus Q as your change in voltage. So let's go through and do this. Okay, what is your changing kinetic energy? The final kinetic energy is 1/2 mv squared. Minus, what is your initial kinetic energy? 0. Equals. Okay, what charge am I moving? An electron, which is a minus E. So this, the charge I'm moving is minus E. Now, what's your change in voltage? Yeah, when you buy a battery here, this is like 5 volts or 10 volts. What that is, that's the voltage difference here. And since I'm going from the negative side to the positive side, it's a positive change in voltage. So this would be then times your battery. Your battery. Okay. So what I'm getting here is that this V is going to be E via the battery times 2 over M square root. If you work this out, okay, what did we say is the charge of an electron? Right, have we now? That's going to be close to the math, the mass, and it's actually closer to Planck's constant. Okay, so it's going to be 1.602 times 10 to the minus 19 coulombs. We'll get rid of the coulombs. Okay. The change in voltage on the battery is going to be 10,000 over. Then the mass of an electron is. Yep. And that equals some velocity here. Now, this is actually used for something. Anyone know what this is used for? Okay, at some point, depending on the engineering you have, you're going to probably have to take Scott Mister's class in X-ray diffraction. So if you want to make X-rays, this is how you make X-rays, and I want to show you how this works. This is actually what produce X-rays. This is why if you're a dentist, when you go and have an X-ray done on your mouth, it turns out the dentists have actually some variation on this of how they actually make it. But I'll show you how this actually works. This is the basis. For X-ray production. Okay, so first of all, I have to tell you a rule. I'll explain the rule at the end of the class, right? I'm just going to give it to you. I'm not going to tell you why it works. Okay. We will see. So first, the one idea. And here's the idea. Whenever an electric charge is accelerated, it emits EM radiation. Okay. So in other words, if I have, let's say this, I put electric charge on this little marker. If I wiggle it like this, I'm accelerating it. That oscillating charge is going to emit EM radiation. That's actually how antenna for a radio station works. You basically have current, you run up and down the wire like this, and as you run up and down a wire at some frequency there, it's going to emit actually radio waves. That's actually how they work. So what's going to happen here? Let's figure out why this is doing what it's doing. So usually over here, this side is actually tungsten. So often what happens is this side over here, this is tungsten. It doesn't have to be what it often is. You hook up your battery, and often this is like 10,000 volts. You have your electron and it goes like this. Okay, I want to basically blow up this part here. So if I blow up this part here and look at it, what would I have? I have basically all these tungsten atoms here like this. These are the tungsten. Right off the board. And tungsten atoms. And these right here, these are the electron cloud. So if I have an electron, and if I smash it like this, as that electron gets really close to that electron cloud, what's going to happen to it? It's going to see that negative electron cloud and do what? Yeah, it's going to actually, it'll try to repel, meaning it's going to actually rapidly deaccelerate. So this electron here, this electron rapidly deaccelerates. And in that process, it emits EM radiation. What it's going to do is going to do that, and then in the process, it emits X-rays like this. So that's how you make X-rays. Take an electron, accelerate some thousands of volts, smash it into a target. What'll come out will then be X-rays. Okay. So this electron rapidly deaccelerates and emits EM radiation. In the form of X-rays. Okay, this is given a nice little German name. Okay, usually in science, if you want to make something sound more sophisticated, you have two choices. You put it in Latin, or you put it in German. In this case, German wins. And it's called Bremsstrahlung, which is German. Is like, I know like 5 German words. This is one of them I know. And Bremsstrahlung is basically the German word for braking radiation. So this right here, this radiation, this is called Bremsstrahlung. It's just German for braking radiation. Okay, how did OTV sets work? With those OTV sets, you had those big cathode ray tubes. Okay, how did they work? Basically a similar principle. You have an electron gun here, and that electron gun would basically take the electron beam, and you basically put a big voltage here. And you're going to smash the electrons into the screen, and then you basically raster the electron gun like this. And there would be phosphorus on the screen here like this. Okay, and those old screens, they always told you not to sit too close to them. Why would you not want to, let's say you're a kid, you know, get your face right up to the TV set. Why did your parents not want you to do that? That's entirely because it's giving off radiation. Okay. So if you get really close to here, there's a low level radiation, X-rays. And that's why people, they told you not to do that. I don't know how really anyone survived in the past, really. Did you ever see jarts? That's great. They had these rings, and then you'd basically have these like very, very large arrows that were weighted with a really, really sharp point. You toss them like this, they're like horseshoes with a really, really sharp point. It's called jarts. Oh, it's great. You know, probably people lost eyes on that and just, hey, let's get a really big, heavy, sharp object and let's throw them on both sides like this. Nothing could be wrong with that. So, questions? Okay. So that said, so that's kind of a theoretical portion for a while. What we want to do now is actually start looking at some practical aspects here. So what we want to start doing is actually looking at circuits. And so we want to look at just regular circuits, then capacitors and circuits, and then capacitors and then regular circuits, and you can get really kind of neat things. And why don't I do what I almost never do, since this is going to be a brand new topic. Why don't we stop it here, and then we'll start on tomorrow. What we'll do is actually start with circuits. Have a good day. Again, look over your exam. I will let you do up to 4 of the problems to get back some credit. What I'll do is I've never done the same thing twice with any of these when I've done this. But again, to stipulate, the little catch is you have to come by with your exam. We're gonna go over it to make sure you master this because this stuff isn't going away. And you're gonna sit again on the second test. And then when we get to magnetic fields, it's basically gonna be the magnetic version of this stuff. So it ain't going away. And my generosity, I'm only generous once, okay? So if the second one doesn't go well, the second one just doesn't go well. Okay, so yeah, I really want you to completely master this material. Okay, have a good day.